boring because today is the pure NARS day. Okay, I'm going to teach in the morning. I'm going to teach in the afternoon, and also I will have office hour in the evening. Then I will be done. Okay, then it's the other guy's job. So what is left are the top layers of the system. We already covered from 1 to layer 4, which in my terminology is called forced outer inference. Why? That's not exactly the same as what we call forced outer parametric calculus. Okay, because this is a term logic, so the context is different. But the basic idea remains the same. When we say it's a forced outer in term logic context, you see I have been drawing this all the time, right? So that you have two terms linked together by a copular. Now we have more than one type of copular, but it's still in this picture. When they're related to each other, this whole thing is called a statement. And on the other hand, this one are called a term. Okay? So in this context, it's clearly separated, between what is a term, what is a statement. And then truth value is attached here. Okay? So it's clean and nice. But this representation has its own limitation because for more complicated knowledge, we want to treat a statement as a term. That is what this layer is about, okay, the very beginning. So clearly in that situation, you see if this one or both are terms, then the system should be able to have statement of statement. Okay, so that's why it's not first order anymore. It's called higher order statement because it's a statement of statement. Okay. Actually speaking, we can actually separate, say, second order, third order, and so on. But for the current design, later I realized it doesn't really make much difference. Okay, so I will just put all of them under the name of higher order statements. So at the very beginning, the idea is to treat a statement as a term. And you see here I have examples about that. First, the simplest example are the relations, conceptual relations, which are traditionally in philosophy called propositional attitudes. Okay. Examples. I guess the best known example, I don't have a list here, are things like know, believe, think, guess, and so on. You see, when you think about those terms, it's always between somebody and something. And that something is a sentence by itself. You see, I believe, blah, 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 you assume, blah, 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 all those kind of things have the same structure. Okay? So it's kind of like, instead of have a sentence as a top level or statement as a top level structure, instead this thing becomes the object of okay. So clearly here we can use the trick we play in layer 4. That is, we take this as a relation, right? Whenever you say know, it means someone knows something. So that we say this is a product which is a special case of this. Okay? Or sometimes it's maybe more accurate to use an instance relation. But now the new idea here is, okay, here we still have, if we don't want to use pronoun, we use just a proper name. Someone know something, and this something now is used kind of as a term which has the relation with this, which is that. Okay. So you'll see, as soon as we allow a statement to be used as a term, this kind of thing can be already naturally fitted into the current structure. There's nothing else to be added for those propositions, okay? Or for those relations. So for those of you who are familiar with AI literature, you know this kind of thing, especially know and believe. Has been studied by logicians and AI before, but their treatment is very different from mine, where they usually define this or something else as a constant in the logic. Okay? It's kind of like introduce another kind of like a copular or something like that. Okay? And then they define, say, axioms or some theorems according to the intuitive meaning of those things. Okay? So for example, they say if you know something and that something must be true or something like that. Okay? What I'm doing here is very different, because according to the idea I introduced last time, this one, as a relation, is an acquired relation. It's not a semantic or syntactic relation with a fixed meaning. Okay? In other words, what know or believe means to the system need to be learned from the system's experience. And different systems may actually have more or less different opinion about what those things mean. Okay? So that's something I must mention, because otherwise people will get confused. So for example, this is a better structured for example. John knows that the earth is round. And the earth is round is a sentence by itself. Now is a proposition. It's a statement which have a relation with John, which is an instance of on. So, and also you'll see this structure can be repeated recursively more than one level, which also there's actually no limitation in the system about how many layers you can have or level. You see this example. We can have something like Mary believes that John knows that the earth is wrong, right? And then you can say, Tom guess Mary knows that blah, 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 blah. You can make it more and more and more complicated. Okay. But in reality, of course, when it's getting too complicated, the system will have problem to process it effectively. So within the system, we use a control mechanism to disencourage the use of this kind of thing, even though logically speaking, it's valid. Okay.
Is the syntactic complexity?
Yeah, the syntactic complexity will increase clearly, and then it will have a low priority, everything else being the same. Okay. Unless you push it very hard, say, for some reason you will have to remember this structure. So that is this. And again, as I mentioned here, higher order means different things in predicate calculus or predicate logic. Higher order means a predicate of predicate. Okay. Here it means statement of statement. That's actually very different thing. Very different thing. Okay. So that many higher order statement, higher order proposition in predicate calculus actually will become fourth order here. Then on the other hand, the first order thing here may become higher order things here may become fourth order things in predicate calculus. So that's this. The other way around is also possible. That is, not only we can treat a statement as a term, we can also treat a term as a statement. Okay. You'll see here I have an example. The simplest situation is, in principle, you see a term is just a name of an internal data structure, right? So of course you can give any statement a name. Okay? Just no matter what long sentence I have, I just say, just to make things simple, in the following I'm going to call it A. Well, that's always possible. Okay? And then what? Is this thing a term or a statement? Well, it's kind of like, well, depend on how you see it, right? So also, you see I have some other examples. Columbus believe, that's clearly, we are talking about some kind of statement, which in this case, I can say that that's equivalent to the Earth is wrong. So, on the other hand, there is still a difference between statement and the term or other terms, like for example, Columbus sheep. Well, that's different from Columbus belief because the sheep is not a statement. So the real difference later we'll see that syntactically speaking, it doesn't really matter whether you really have a subject-predicate relation anymore. Okay? Because you can use a single term to represent such a relation. So the real difference later when we talk about statement versus term is that a statement can or normally has a truth value. You can talk about whether it's true or false or to what degree it's true. On the other hand, a normal term, if it's not a statement, it doesn't make sense to talk about whether it's true or false. Okay? So for example, this thing, okay, you cannot talk about whether it's true or not. But the statement say this is white or this is black. You can talk about the truth. Okay. Again, the other examples. So that's the actual difference. And some people actually ask me later after they see the grammar rules, and they say, according to the grammar rule, a statement and term are actually the same thing. Which, yes, syntactically speaking, okay? This can be used as a term, this can be used as a statement. But still, whether you can talk about the truth of that thing, change from situation to situation. So there is still a difference, but not pure syntactic. Okay? So what else? So that's the simple part. For this part, you'll see we don't really need any new inference rule. Okay. Everything else we covered before can be used in this way. For example, we can have deduction, induction, abduction, where the thing involved is not a normal term, but a statement. Okay. For example, if you can establish the similarity between one statement and another, then you can use analogy so that if you believe this and this is similar to that, then you should also believe in that to a certain degree, that kind of thing. Okay. Just like before, you just, as far as you allow a statement to be used as a term. So the second section is really about to introduce new things, which is only applied to statement. It doesn't apply to normal term. Here, again, by statement, I mean not necessarily have this format, it can be this, but it's something you can talk about is truth value. Okay. So,
why don't you need something to take out sub-terms out of a statement, just like you did with the product relationship?
What do you mean?
Well, if John believes that planets are round, then he also believes that the Earth is round, right? So, how do you make that inference if the planets are round thing is?
I see. It's the same thing, like what we did for product. So that the same sentence can be rewritten in three different formats. You can say this is belong to whatever Tom believes. Okay? And also you can say Tom belongs to the group of people who believe the Earth is wrong. And then you can do inference on Tom, on this statement, or on the overall structure. It's just the same as before. Does that answer the question?
Well, I didn't want to take out. So, okay, in this case, you got the image and structure of
Uh-huh.
I think, in order to get terms out of a product
Yeah.
compound, right?
Yeah. Yeah.
How do you get S and P in?
Well, the same thing you can have. Something like that. This basically means that whatever for Tom's knowledge, and this is part of Tom's knowledge.
And if A is a type of S, how do you just do an A?
If you say that, how this thing can get into this? No, I will not. I will have to treat this whole thing as a term. Okay? And for that kind of inference, that we need much more complicated mechanism. Yeah. But in certain situations, it can be done, but not this simple. So now we are going to introduce two new copulars. As I said before, I mentioned that within the system, in the current implementation, actually there are only 4 copulars. Okay? We already see this two. And in the following, I'm going to define this and this. Okay? Just for the higher order inference. The first one is called implication. The second one is called equivalence. Intuitive meaning, well, as you can guess, the first one is if then. The second one is if and only if. Okay. Think about them. Those relations only hold between statements. So the first part and the second part both need to be able to be to be evaluated for its truth value. Okay. Like in programming language, if you say if then, and then the if part must be a condition, right? It's either true or false. Okay. So the intuitive meaning is pretty simple, but the accurate definition is different compared to how this is handled in propositional logic. I hope you still believe or remember in propositional logic, what's the truth table of implication? P implies Q is false only when P is true and Q is false, right? In all the other situations, it's true, right? So that's the thing you learn in day one in propositional calculus. But this one, even though it also intuitively means if then, is not defined that way. Okay? Let's see how it's defined. This is defined if and only if S2 can be derived from S1 in finite number of inference steps. Okay? So S1 implies S2 if and only if. You see, this is derivation notation in logic, so that from this one you can derive the other. So it doesn't necessarily to be in one step. More than one step is okay. The intuitive meaning is do this, and also that also means you see this is the definition, right? Another form of definition of implication in predicate calculus. That is, this one is equivalent to not P or Q. Once again, that's not true in now anymore. Okay. Later we will see more about why I don't want to do that. So first, let's see. Okay. What I mean. Once again, let's concentrate on the binary case, okay, inheritance logic. S implies P means P can be derived from S. Okay, that's the intuition. That's also the intuition behind whenever we call if-then. That is, whenever we know the condition is true, we know that the conclusion is true, applies. Okay. So the intuitive meaning behind this one is still the same. It's just how to accurately define. So because of that definition, you can directly see this result. So this relation is clearly reflexive and transitive, right? From everything you can derive itself, well, it's the same thing. If A implies B, B implies C, then of course A implies C. You can do it in more than one step. Okay. And also this relation is defined among all statements. Okay, between statements. Statement here means that whatever you can talk about truth value. Okay. So then what? Then it should remind you what we have done in the first level for the inheritance coupler, because the inheritance coupler is defined exactly by those two properties, reflexive and transitive. Okay? So now you see, I'm writing it in this way for a reason. Okay? So this one and this one are perfectly parallel, or not, well, almost perfectly parallel to each other. And this is between two terms. This is between two statements. But statement is a special type of term. Okay, so we can see this as kind of like a special form of, or a variation of this one. Okay? And this one is just two-way inheritance. This one, as you can guess, even before I define it, is two-way implication. Okay, you imply me, I imply you, so we are equivalent. Okay, meaning that we have the same truth value. So then what? Then I'm going to skip all the following definition, directly show you a table which summarizes all those results. It saves us a lot of time. And this is another reason why I like first order, why I like term logic. Okay? You see, this is the isomorphism between first order and higher order. Term in first order corresponds to statement in higher order. The inheritance corresponds to implication. Similarity is correspond to equivalence. And you see here we have something called the subject and predicate, which are the terms linked by the coupler. Here what we have traditionally is called antecedent and consequent. Okay? Or in computer science we say this is a condition, this is the result or conclusion. It's just a terminology thing. Okay? But again, you see, in first order, we talk about extension and intension. What I mean, extension, you see, for this is everything you see on this side. Okay? Intension is everything on this side. Higher order, we can do the same, which corresponds to the traditional term, sufficient condition and the necessary condition. Okay? So see, if this is true, we say this is a sufficient condition of this, this is a necessary condition of this. Right? That's the traditional usage of those. Then what also extensional intersection, which is this. Intensional intersection, which is this. Naturally correspond to conjunction, which is this. Disjunction, which is this. Okay. The isomorphism is good to such a degree that in first order predicate calculus, if you go back to the book, you pick an arbitrary theorem. You just do this replacement. Okay, you replace all the first order terms into the higher order terms. The result is still true. Okay. Why? Just because it's perfectly parallel. How you prove it? That one you can prove it the same thing in the higher order. You just replace the term accordingly. Okay. So that gives us a whole bunch of inference rules. You see, this is the table. Kind of like for free. Okay. And then now let's see what's the new grammar introduced in layer 5. Well, first you see we allow a term to be a statement. Just to avoid the confusion, usually whenever you write it as a term, you add a parenthesis. So because it's not on top level anymore, it's embedded in another bigger one. So to avoid confusion about the order of operations. Even though that's optional, of course. On the other hand, a statement can be a term, as I said before. You can give it a name, then it becomes a term. So in this level, actually, these two become more or less the same. Okay? But semantically, there's still a difference. And also, that's the compound statements. Here, you can see it looks very familiar, just like in predicate calculus. So you can introduce, this is a negation, which we haven't mentioned yet. That need to be handled separately. Okay? This is and or conjunction. This is or disjunction. Okay? Which are defined exactly in parallel with how you define union and intersection, or extensional or intentional intersection. Okay? And now we also got two new copula. Which is implication and equivalence. So that's the grammar of layer 5, okay? Which is pretty simple, but now it becomes much more powerful in the previous layers because you can build, you can talk about statement of statements. Okay? That's absolutely necessary. And then you see this. The question is about negation. We haven't talked about it yet. Okay, negation needs special treatment. We have a separate section after this one. I'm going to talk about negation. Okay. Yeah. For now, you just need to know that negation is operator. It only take one argument. You only negate one thing. Intuitively say no, that's not the case. But we are going to talk about much more about that. So the rules, let me summarize the case. You see all the rules. For example, the first order rule for deduction, abduction, induction, exemplification, and convention, they will be modified in the same way. Okay. For example, yeah, you see. What we have been seeing all the time is this. And this is F1, C1, F2, C2. And this is provided by the deduction function. Okay? So basically, you remember that frequency is this two multiplied together. Confidence is all of them multiplied together. So that's the rule we introduced in layer 1. Now in layer 5, easy. Okay? Now, of course, now this must be something you can talk about this truth value. It's not a bird anymore. Okay, it must be, say, bird can fly, bird is an animal, blah, 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 which will be here or here or here or here or here. And then this part, exactly the same thing, the same function. Why? Just because you can establish the result in exactly the same process. Okay, so how about the other guys? Well, induction. As you can guess, the same argument. And this now is this statement provide one piece of evidence for the conclusion that whenever this is a case, you can say that is the case. Okay? Be careful this is not the same rule as first order rule. Formally, the formal definition is different, and the semantics is different. But it's kind of like a perfect mirror image of each other. Okay? Or we say, mathematically, we say that's isomorphism. So the same thing for everything in this list. And for the second layer rules of those things, for example, yeah, if this is equivalence, then of course we have the same thing using the resemblance function. The same. Okay. Analogy is the same, comparison is the same, and layer 3, we're talking about compositions. Once again, if you know this, you know this. And in layer 3, you know you can derive. Previously, we can derive right? Now in higher order, you change this into higher order, and you change this into conjunction. Same rule on this side. Okay. So certainly you get a whole bunch of stuff for free, which is also applies to backward inference, which is like something you know this, you want to know about this, and you already know this, then that means you want to know about this. Okay. If you get answer here, and that one plus this one will provide answer for this. So all the backward inference rules can also be obtained by this simple mapping, okay? Which, by the way, all the rules are summarized in the appendix of the book if you want to see the whole list. So that's the rules in level 5 you get from the isomorphism. There are a whole bunch of other rules which just simply treat the first order case and higher order case exactly as the same. You don't even need a mapping. Okay? Those rules are the one, I think I mentioned it somewhere. For example, there's something we didn't mention. Yeah, for example, the layer 4 rules between the image and the product, which we already showed an example. That's exactly the same rule as the first order. Okay? You don't even need this replacement. And also some other rule, for example, the revision rule. Okay? If you have two equivalence relation, you can also merge them together. Exactly in the same way. Or actually, now we can summarize the revision rule in a better format. Instead of writing that, we just say we have a statement with a truth value, the same statement with another truth value. Then we can get a statement, use the revision rule. Okay? And whether this is fourth order, higher order, it doesn't really matter, as far as they have the same content. Okay? So that's another situation where some of the rules can be directly applied in the same form to both first order and higher order. Okay? Yeah, it's mentioned here. So those things will be directly used. But be careful whenever you use them. For example, the layer 4 rules, they are still defined with respect to the inheritance relation. Okay? Remember when I say something, okay, Tom knows the Earth is flat or round, the opposite. What we use is still, this is a special case of no. Okay, be careful. You don't want to say because it's a higher order, it should be implication. That's not the case, right? No is a relation. It's not a statement. Okay, you cannot talk about the truth value of that word. It doesn't make sense. Okay? So it's not really too hard to remember which is which. But of course, it does provide some challenge for the implementation, which I'm going to mention briefly later. So that's the second section. You see, the first section just say that for some rules, you can directly use a statement as a term. The second one say that there is isomorphism between first order and third order, higher order. This one introduced something which is really new. That's the only place probably we're going to really introduce something new which we haven't seen before. That is the inference rules which only apply to higher order. It doesn't apply to first order, even though it's related to first order. Let's see why we have such a thing. Such a thing comes from, not from the transitivity and reflexivity anymore, because all those things you can also have it in first order. Okay? Here the specialty comes from the special meaning we introduced, that is implied means can be derived from. Okay? That meaning is not there in the first order. So we don't have corresponding rules for those. So here, but still I want to play a trick. I don't want to define a whole bunch of rules. You see that's, now I guess you begin to see my preference or bias or style, whatever you call it. I would rather not to introduce a whole bunch of inference rules by itself, each one by one. Instead, I try to get a whole bunch of them using the same idea. Okay. Here, the following trick is this. You see that in the system, according to our semantics, a statement, now you see, I use a single letter, okay, to represent a statement, which is possible. A statement has a truth value, okay? Which means what? According to the semantics, once again, it doesn't mean according to the reality of or the world or whatever, okay? We say that this is always according to the experience of the system. Or in other words, given the experience, the system believes this thing to this degree, right? That's what it means. So, in other words, I can say that this result is implied by whatever I know to that degree. Okay? So this is just a different way to talk about the same thing. Okay? But here, this is not a real statement. This is a virtual statement or something I introduced just conceptually, just because to write everything you already know as a sentence, it will be way too long, okay, in reality. But in principle, we can say that, right? We can say, well, in principle, once again, if I really ignore the requirement for resource, blah, 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 I can do that. Okay. But you say, oh, you cannot do that. You already assume insufficient knowledge, yes, and resource, yes. That is why what I'm saying here is a conceptual change in the meta language. Okay, in the system, I don't really go into do that. But I just, when I design the system, I can think in this way. Okay? You may wonder if you cannot really do it, to think it in that way, what difference will it make? You'll see, it gives us a whole bunch of rules for free. Okay? How? Let's see one example. If I know S to a certain degree, I know S implies P to a certain degree. What do you expect the system to derive? What kind of inference? Do we need a new function, or we can use one of the functions we already introduced before? Or intuitively speaking, what type of inference this one is, or closely related to deduction. Yeah, exactly. And I can show you it is deduction. Why? According to the trick I played. Okay? This can be rewrite into this. And this one, I draw a circle around it to say, okay, it's not a real thing. Okay, it's just conceptually speaking, it's just a symbol I use to indicate the current knowledge or the current evidence. But conceptually, it's a statement. So now you see it perfectly fit into the deduction pattern. Something is S is something else, then right? That's the old-fashioned deduction we have defined all the way. But we know this is a conceptual thing, so that I can validly write it. What's that? Okay, it's just kind of like this. This can be added and dropped for free if you really want it. And after you add it, you turn it into a pattern which we have seen before, which gave you an inference rule. And then in the result, you don't mention it anymore because in reality you never use it. Okay, so this is a conceptual thing you can add. So the real inference rule the system is going to see is this part. This is the premise. This is the conclusion. Okay, and this part are introduced to tell you, how does that come from, right? So if we allow that kind of trick, we get a whole bunch of other inference rules for free using the same way. You see, this is this table. This is the one I just showed you. You see, again, whether you call it S or M, it doesn't matter. It's just a variable name. Okay? So if this are the premise, add this one kind of like idealize the condition or something to the second one to turn it into a subject-predicate format, so that we can use the old rule to get this one, and then eventually we drop that. Okay? And intuitively, it also makes sense. It's the kind of rule we do use in daily basis. And similarly, you see, the other way around is abduction. Okay? So if you know this to a degree and you see this happen and you guess, probably that's because this one happened. And that provides an explanation of your observation. Okay? That's a major function of abduction. Okay? You see a lot of things, you don't really know the reason. But you get some explanation which will implies what you're going to see. Okay? And then you believe that thing to a degree, but you cannot believe it too much because this is not a deduction. Okay? This is a special form of analogy again. Okay, if M and P as statement have similar truth value, and you know one of them is true to a degree, then you can say the other one, by analogy, will be true to a degree. Okay? So this is different from the isomorphism. This is we are playing some small trick to turn a new situation into a familiar situation, and which will be justified by the same semantic analysis. So this is another group. This time we are doing this trick to both premises. And this looks more radical. You know P, you know S. Also under the additional condition that you can assume both of them are supported by the same evidence. If you can make that assumption. Okay, this is not universal, it's limited, not like the previous group. The previous group kind of like have no additional condition, okay? This group have the additional condition that is P and S must be supported by the same evidence. So if that can be said, I will just add that in, then it will turn it into a familiar pattern, which will give us induction comparison, and the conjunction and disjunction derived from that condition. And eventually we say, since that's the case, this condition can be dropped in the conclusion so that we just get the conclusion by itself. Okay?
Are you meaning to say that if you've got P and you've got S, you can derive any of those four calculus on the right-hand side there?
Mm-hmm. Yes and no. You can, on one hand, yes, if you check this side, you will see it's pretty similar to what happened in predicate calculus. In predicate calculus, disjunction, conjunction, implication, equivalence are all defined by a truth table, right?
Okay.
So from the truth of S and P, you can derive the truth of each of the structure. Okay? Especially this one and this one, if you check the truth value function, you will see it get the same result. You'll see if one is true, this will be true, but this one will be false. And this one will be true only when both of them are true. It's a boundary condition. But these two are different. Because if you still remember this, induction and comparison are weak inference. It doesn't give you something with 1 as the upper bound of confidence value. Okay? On the other hand, these two are strong. These two can give you confidence close to 1. These two cannot. Okay? So that's one difference between this system and the propositional calculus. That is, if you only know the truth value of P and S, you cannot strongly decide whether P implies S or S implies P or they're equivalent or not. But you can provide evidence for that. That's number one. The number two difference is, as I said, this rule applies only under special condition. In fourth order or in propositional calculus, you can pick an arbitrary P and an arbitrary Q and do this. It's a valid inference. And also, furthermore, you can even do this. Okay? In NARS, no. Because it required this tool to be supported by the same evidence that's the definition, and in reality, what's that mean? Later we'll see that this rule is this group of rules, any of them, is used only when P and S are related in content. It will not take two arbitrary things and try to take their conjunction, disjunction, and implication equivalence. Okay. So in this sense, this logic is not pure truth functional. On the other hand, predicate calculus is pure truth functional. What that means? That means in propositional calculus, you'll see, again, truth table, okay? Only truth value matters. What's the content of this? Doesn't matter. In this system, it's not the case anymore. Okay? If the content are not related, this rule cannot be applied. For those of you who are familiar with logic, it should occur to you this is directly related to the so-called implication paradox, which have been studied in logic for a long time, which is the major motivation for the schools like relevance logic. Okay? Why? Just because it's well known, you know, in traditional logic, P implies Q is true even though P and Q completely have nothing to do with each other. Which sounds really weird, and especially for AI, especially for AGI. That's big trouble. Okay, it's kind of like you already have a knowledge base with millions of knowledge, and this tell you you can pick any two of them and make a conjunction and disjunction is still is a valid conclusion. It's just way too many possibilities. Okay, and also most of the results doesn't make any sense, even though logically speaking it's true. So in NARS, that will not happen. And this is basically a summary about the relation between this, in a sense, the three most important type of inference. Deduction, induction, abduction. Okay? Now you'll see that in this logic, in now, it actually comes in several different forms. But in each of them, they are kind of like related in the same way. Okay? You see, this is the fourth order version we introduced in layer 1. And this is the higher order version I just mentioned. You see, this one is just obtained by replace this single arrowhead into this double arrowhead. Okay? Meaning that you replace all inheritance by implication. And also, of course, the meaning of the term involved also change from normal regular term into statement. Okay? But still, you see the pattern is the same. And also we have a third group, which is what I call in the book conditional rules. It's not necessarily a good choice, but I don't have a better word for it. So I call it conditional. So you see, this is deduction, this is abduction, this is induction. And also, this kind of relationship was first introduced by C.S. Peirce. Okay? He said that you can define induction and abduction by switching the conclusion and one of the premise of a deduction. You see here is perfectly the case. It's even better than his original example. Okay, because it happened in all three situations exactly the same. Okay. So there are a couple of other tricks played in the system because of the meaning. You see, a conditional of a conditional. In this system, it can be proved it's equivalent to a conditional with a conjunctive conclusion, a condition. Okay? Think about that. Intuitively, it is the same. Okay? And this is actually directly related to what Chris introduced yesterday evening about what if you have a model and you have another model which is about this model. Okay? If you remember that. But in this system, I can just his decision is to keep each model to run roughly at the same time amount of time, so he does not allow compound condition. Okay? But I actually in NARS prefer a compound condition than a conditional of a conditional for some different consideration, because I don't really care that much about how long it will take to check a condition in the system. So anyway, that's something interesting right now. And also you'll see that if you take that into consideration, you get another group of deduction, induction, and abduction, which I don't have the time to analyze each in detail, but you guys can take a look, and if you have the interest, you can try to prove. For example, this is deduction, this is abduction, this is induction. Again, this is deduction, this is abduction, this is induction. All of them can be derived from the previous rule by taking, one more complicated statement as a single letter mentioned in the previous rules. So that raises an issue. You see, sometimes people ask me, how many inference rules do you have in a system? The correct answer is it depends on how you count. Okay, so that, for example, here I already gave you 5 rules which all called deduction, which all looks different from each other. But on the other hand, they can be seen as one rule. It's just kind of like different variations. Okay, whether you count them as 1 or 5, it just depends on how you want to count them. And both will make sense. But on the other hand, if you say how many different truth value functions do you have? Yeah, that's a much more clear question. Deduction will be, all the form of deductions will use the same truth value function. So in that sense, I'm using the truth value function to define the type of inference, not the format of the premise conclusion combination, okay, because that may change from situation to situation. So yeah, how many different truth value functions I have? I think it's about 15. You can check at the end of the book. Okay? I think it's about more than 10 for sure, less than 20. Okay, now let's see. Negation needs special treatment. Okay. Previously, you see, we have talked about not, but that's still different from the negation we introduced here. Especially in layer 3, we define this difference. Okay? So you see, M is in S minus P, which means M is in S and M is not in P, right? But at that level, this negation sign is introduced in meta language, not in NARS. Okay, this is in NARS, but this is not negation. Difference is always relatively defined between two terms. On the other hand, negation is applied to one single argument, which is the statement I need to negate. Okay, there is a subtle difference between the two. So, and also, by the way, in fourth order, there is no such a thing as the complement of a term, not like in set theory. Okay? In set theory, you can say the complement of a given set, which kind of like include everything but not the elements of A. Okay? In NARS, that's not allowed. Because there is no universal set assumed. There's no such a thing as everything. Okay? Even if you define a concept of everything which is allowed, it doesn't really still cover everything. Okay? So that's why here we need some special treatment. Part of the treatment is pretty natural. First, how to define negation? Well, it's defined in this way. The negation of S is defined from S by switching the positive and negative evidence. So it's kind of like the opposite of S. So the positive evidence of S will be the negative evidence of its negation, and the other way around. Okay? So I hope that makes sense. And as soon as that's the case, you directly get the truth value function used by the negation rule. And also, it implies that double negation will cancel out each other as we expected. Okay? You switch twice, you go back. And a whole bunch of other things like De Morgan's law still hold and so on. You can check that. And this is the truth value function for negation. Okay? You see that if you switch positive and negative evidence, then the frequency of the conclusion is 1 minus the frequency of the original statement. That's obvious. Okay? And the second part may be counterintuitive to some of you at the beginning. The confidence level remains the same. Meaning that, but if you think about the definition, it has to be the case because you only switch positive and negative to between each other. The total amount remains the same, right? So you try it 5 times, no matter it's yes or no. The negation is also supported by the same amount of evidence. Okay? So that's it. And then there are a couple of other rules which only take one premise like this one. Okay.
Is that x right at the end of the, is that a multiplication?
Pardon?
1 minus f1 multiplied by c1, is that correct?
This one?
No, no, next, right there.
This one?
Right there. Next to the c1 there. Is that a multiplication?
Oh, this is multiplication, and this is not introduced in this layer. Actually, I just summarized them together because these rules are related to each other. This is actually introduced in the first layer. It's a special case of induction and deduction, abduction. Okay, I skipped it just because we don't have the time. This one doesn't have anything to do with negation. But the interesting about this one is, this is traditionally called conversion. That is, if you know A is P, A is B to what degree you know B is A. Okay? Of course you don't know, but they give you some evidence. And this one, the interesting thing about this is, this form of inference only provides positive evidence. And also the amount of positive evidence is the product of the frequency and confidence of the premise. The explanation actually is in the first, in chapter 3, I think. It's in layer 1. You can go back there. What I want to talk about here actually is this rule. This one, if you still remember the Raven's paradox I mentioned, whether when you see this, you should believe a stronger need that Ravens are black. That's directly related to this. Okay? You see, in traditional logic, S implies P, and not P implies not S. They are logically equivalent. You can easily get that result by rewrite them according to the definition. You see this one is what is this. Okay. How about this one? Again, okay, it's this, and this cancel out each other. So this is, they're the same thing. Okay. So that Ravens are black and non-black things are not Raven. They're equivalent in first order predicate calculus simply because of this. Okay. But I already told you that it raises some problem. Okay. Now this is a formal explanation how I analyze that problem, why that problem doesn't appear in now. You see that this inference or these two statements in now only share negative evidence. They don't share positive evidence. Okay. That's actually my answer to the Raven's paradox. So the traditional equivalence is still correct in traditional logic, because in traditional logic, in binary logic, actually true means no negative evidence. Think about it. True means no negative evidence. Whether there is positive evidence doesn't really matter in first order predicate calculus. Okay? Especially, for example, this one, if you write it into this form, for everything, if it's Raven, it must be black. Okay? If you find something which is indeed Raven, but not black, that's negative evidence, then this will become false. If you never see this kind of thing, this is true. Even if in that world there's no such a thing called Raven at all, this will remain to be true by definition. Okay? It doesn't really need any single piece of positive evidence to show you indeed there is a Raven which is black. You don't need that in first order predicate calculus. So because in that logic, only negative evidence matters. If two things have the same amount of negative evidence, they will be considered as equivalent. But in this model, truth value depends on both positive and negative evidence. So this sentence, or we say ravens are black and non-black things are non-ravens. Well, here I cannot really say non-black thing. Well, you can say that bird, which are not black, right? Use the difference. And bird, not ravens, or object, not black. Object, but not ravens. You can say that. But those two sentences will have different truth value. They're not equivalent anymore because they have different positive evidence. Okay? So this rule actually shows you exactly why Raven's paradox will not appear in the system. So there are a whole bunch of other discussion about negation, which I'm going to skip. And this is a summary about how some of the results we have proved before can be used as inference rules in the system, which need for us to have a much better, more clear idea about how the logic I introduce is related to the traditional logic. So this is a good place to summarize them. You see, so far, we have discussed at least three logic involved. Okay? Non-axiomatic logic, that's the subject matter of the book. Okay? Then I also have a inheritance logic, which is the idealized version or the binary version of it. It's its foundation. And also, I have been using propositional logic all the time as a meta language. When I talk about the definitions and theorems, blah, 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 right? Then here, first I discussed the relationship between these two. Well, clearly the first one assumed insufficient knowledge and resource, the second one doesn't. Okay. But they still have some similarity. Also, the second kind of like provide a limit situation for the first one to convert into when it gets more and more and more resource and that kind of thing. And also in terms of inference rules, you'll see I already said that there are a whole bunch of rules called the strong rule. That's the rule have one as the upper bound of confidence value. All of those rules, if you just drop the number, okay, and to turn everything into binary, you see there are valid inference rules in the binary version of the system. On the other hand, the weak rules like induction, abduction, and so on, if you drop the truth value function and it looks completely, it's just a fallacy, okay, it's not going to work. Concrete example is this. Right? In now you're going to have this calculation, but in IL you just have this. It's correct. But if you turn this around to make it induction, then only when you give the truth value function it can be justified. I will say to a degree that give you provide this evidence. If you drop those things and make it a binary rule, that's simply wrong. Okay? There's no way for this to be derived from this. So that also gave us the relation between the rules, and which this conclusion actually is very useful for the following layers when I introduce new inference rules. Later I will go back to this topic. And this is a summary of the similarity and difference between the binary version of my logic and the propositional calculus. But most of the point I have already mentioned before. This is just a place where I summarize them all together. You see the truth table basically for these three are more or less the same. It just make it kind of like the content need to be relevant. That's the only thing required. On the other hand, for this and this, the treatment is very different in these two logic. Okay. Actually, I always believe, if in propositional calculus, all these five are handled together with the same status, to me is not a good idea. It's good enough for mathematics, but intuitively speaking, these two and these three, they're different animals. They actually behave very differently in human cognition. They serve different roles. Okay? Especially here, furthermore, these two are more similar compared to that. Okay? So that's how it's handled in my system. These two are kind of handled in a perfectly symmetric manner. Okay? These two are handled in very similar manner. This is two-way, this is one-way. Okay? This one is a little bit special, but still, these three will give you compound statement. And these two will kind of like build a relationship, build a relation between the truth value of statements. They serve very different functions. So there are a bunch of other discussions if any of you are interested, but I will have to skip them. That's basically layer 5. In terms of the involved inference rules, actually layer 5 is the biggest layer. If you check the examples, there are a whole bunch of them, just because there are a lot of inference rules introduced in this layer. But on the other hand, conceptually speaking, it's not that complicated because all those rules are introduced by group, okay, not individually. So as far as you can get a couple of basic idea, you should be able to understand. Okay? So here you'll see, once again, toward the end, I have the links to the examples with rough English translation about what each inference rule is doing. And one way to really understand it, once again, is print out this page and compare it with the corresponding fourth order rules to see the similarity and difference between them. That will be interesting, I hope. I think I will take the break earlier so that we can, after that, we will go into layer 6. So let's take a break until 10. Layer 6. Here the key idea. You'll see once again in each layer, what I have been doing all the time is nothing but to expand the scope of what can be a term, roughly speaking. Of course, when that scope gets expanded, there are some other things need to be introduced from time to time. But this is basically the biggest topic at each layer, and which is also true for 6 and the layers after it. So in this layer, we expand that by allowing a term to be a variable. First, what that mean? Okay. What it does not mean is, it can change its meaning. what I already told you that according to the semantics used in NARS, the meaning of every term can be changed, right? Because when you have new experience, of course it changes the meaning. So it doesn't really mean that when I say it's a variable term. Instead, another thing is, I have been saying that every term is the name of a concept. Okay? So it's the name of a concept which is an internal data structure. Okay? So that's the place where variable term is different from the other terms. Variable term is not the name of a concept in its original form. Okay? So the other terms are constant in the sense that each of them is consistently tied up or connected with a fixed or determined concept. Okay? So this bird always name this data structure, which is the concept bird. You know that it contains all the task and belief with bird in it. Okay, bird is animal, and bird, blah, 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 blah. What is a bird, and so on. So this one always name this one. Okay? On the other hand, a variable term is more like a variable in the mathematical sense that, for example, x, it doesn't fix, it's not fixed on anything. On the other hand, it can be anything. Okay? So that in this system will be something like, this name can be used to represent this concept in one situation. It can also be used for another concept, which actually is called water, in another situation. Okay? What's the intuitive or internal or intrinsic meaning of x? Well, there is no such thing. It's just a variable. Okay? It's in that sense we say there are variable terms and they are different from the ordinary or normal or constant term. So that's the first thing. And in a sense, we have already seen some variable in this system. For example, the query variable, we have seen that before. Say, there's a question, I can say, what is a bird, right? So that's a question the system can be asked. So what is this? This is actually, it's already a variable in that sense. It's a placeholder and needs to be filled in by the system itself according to its knowledge. Even though I didn't say too much about that, it's just because that's pretty simple, it's understandable. Okay? Now we are doing similar things, it just make this much more complicated. So, other related topic, for example, intuitively, it's like the pronouns in natural language, like it, that. Okay? Or in mathematics, it's like x and y. So, furthermore, there are actually three major types of variables in the system. I start with a simplest case, say a query variable or something like that, which can appear in a question. And it needs to be filled in by the answer. Okay. And you see that in the current implementation, all the query variables start with a question mark as a prefix, followed by either by a letter or by a word in general. Actually, in the implementation, later we'll see, it's all formalized into a number. So all the variables are actually numbered within the system. Even though on the user interface you can say x and y, but later when you get into the system, you'll see it's translated into number 1, number 2, number 3, just to make the processing easier. Okay? One thing about variable is, you see, the name doesn't really matter. Okay? You cannot change a bird into something else without get the system confused. Okay? In the middle. On the other hand, whether your equation, we know that whether you call a variable x or y, as far as it's not used also for something else, it doesn't really matter. Okay? It doesn't change anything. So that is why it's possible to rename them all by numbers within the system without causing any confusion. So that's a query variable. Then the other tool is very similar, but not the same as this. Okay, I assume you are all familiar with first-order predicate calculus. This is universal and existential variable. This means for every x. This means for some x, or there exists x. Okay. So we need the same thing here, but not exactly the same. Okay. All the variables in this category start by this pound sign. And by the way, there's another thing that makes it a little bit messy is after I have the book draft delivered to the publisher, later actually I changed my mind. Okay, in the current system, actually I use two different symbols for those two types of variable. Okay, but for now I will just follow the book, and then I will tell you why I make that change. That matters if you try the example. Okay. Because the example is already using the new convention, so it's not exactly what the book tells you. Okay? But it's a notational change. It's not conceptually. It's still the same thing. Okay? So following the book, we say that both type of variables share this pound sign as prefix. So everything starts with this, okay, something like this. They're variables. Okay. And furthermore, what we call independent variable is intuitively similar to this, even though not exactly the same, which looks like just like that. All of those will be independent variable. On the other hand, dependent variable intuitively correspond to there is such a thing, which is marked by what actually in the book is marked actually by a dependency list. Because if it typically depend on something else, then something else typically is independent variable. Which is like in mathematics, you have variables, some variables are functions of other variables, right? So the same thing here. So independent variable is represented in this way. Dependent variable, on the other hand, is this followed by a dependency list, which can either be empty or can be the name of another independent variable. Okay, that's why it's called dependent. So mathematically, you can think of that as a function. But we know there are special functions which doesn't depend on anything. So it's like a constant function. Okay? So this will be dependent, this will be independent. And actually in the new implementation, this is independent, this is dependent, and the dependency list is not mentioned. So that's the change I later made. Actually, this is not a big deal. The major decision is later I realized that actually I can implement it without dependency list, which makes things much easier. But if I do that, I will have to use another way to separate this two. That's why I switch to a different letter, okay? Different symbol. It's not because the dollar sign looks better. Yeah? Anyway, here I will explain why I need a variable. There is actually several reasons. The primary reason is this issue which I mentioned before and also discussed with some of you yesterday evening. That is a major decision in this logic from the very beginning is to merge the evidence from extension and intention. I hope you still remember that, right? So I said to decide the truth value of this, it can be done by deduction, it can be done by induction and abduction and so on. You see, whenever we do induction, then typically what we are doing is this. We find an instance of S and to check whether it's also an instance of P. If it is, it makes this higher, otherwise it makes it lower, right? So that's extensional evidence. On the other hand, we can also compare the property of S and P. And to say, okay, if they share some property, and then this is higher, otherwise it's lower. Then what? Then from the truth value itself, okay, you cannot really tell where it comes from. It's just a number. And it can be this, it can be that. Or more typically, it can be a mixture of the two, because typically each conclusion is supported by evidence from different sources. Okay. A major decision made in this model is to merge them, which have important implications. For example, the conjunction fallacy I discussed yesterday. Okay, that's exactly the situation, that where all the evidence actually come from here. Okay? But if you interpret it in this way, it's a fallacy. But according to probability theory, you can only get information in this way. So that's why the human behavior is judged as a fallacy. Okay? But if you can merge them, then that's a different story. Okay? So this is an important decision, but also a controversial decision. Because from the very beginning, there are people who say that, yeah, you're mixing different things. Okay? It is. Okay? What I'm saying is I have a reason to do that. But at the same time, I know from the very beginning, you cannot always do that. Okay? In many situations, you have to clearly separate the extension and the intention. But I think my solution will be, yeah, merge them in layer 1, but if you really want to separate them, I can do that. How? Using variables. Okay? You see that this one, according to my interpretation or semantics, I already told you that what it actually means. It can be read in two different ways. One way, if you read it in a pure extensional format, it means what? Whatever in S is also in P. Right? If I use a variable to indicate that whatever, then right? If this thing is in the extension of S, implies then it's also in the extension of P. The intentional sentence of the same relation, a pure intentional representation is what? If P has a property, then S has the same property. Okay? So this is a pure intentional representation of this relation. This is a pure extensional. And this one, on the other hand, can be seen as these two merged together. I mean both of them. And after they're merged, they stay merged. You cannot tell which is which anymore. So the full picture or the full story for NARS treatment is this. it can't treat extension and intension separately. They can't combine them together. And the combined version is, you see, it's much simpler. It's the default, and also it provides you the way to use one for the other. That's the major reason I want to merge them. It's not because it's easier to do, okay? It's because I believe we typically use extensional evidence to make intentional judgment and the other way around, as shown exactly by the Linda example in conjunction fallacy. Okay, that's actually evidence to support my conclusion. But on the other hand, if we really need to separate the two, I can do it in this way. So what the system will actually do is this. Whenever you really see A implies A is an instance of S and A is an instance of P, what the system will actually produce is the system will actually produce this one, both this one and this one. It will not produce this one, because this is extensional evidence. Okay? To show you I'm not claiming things that's not really done, you can see the code. Okay? If we actually go into, where are they? You see, this is where the examples are. You see, I keep showing you the edited version just to separate the layers. Now, if you really take a look, it's the unedited version. This is the real thing, okay? The real complete input and output. When I tell the system this, that's exactly this pattern, right? You see, it produces a whole bunch of stuff. This the induction we introduced in layer 1, right? And this is the comparison we introduced in layer 2. And this are the composition we introduced in layer 3. And finally, these are the variables introduced right here in layer 6. Okay. You'll see that in this situation, actually the system is doing all of them all together. But after a while, the system, that's the control mechanism which will decide which of the conclusion will actually be remembered by the system for a long time. Okay? So for example, after a while, if for some reason only this one turned out to be useful, and this one later become confusing because for a certain problem, extensional information and intentional information must be separated, then this one will become a low priority thing. Even though, be careful, truth value doesn't change, okay? Truth value doesn't necessarily change, but frequency, truth value may change, may not, but frequency, priority will be decreased for sure. Okay? And this one, on the other hand, will be remembered, so the system will remember the extensional version. But in another situation, maybe this one is more useful and also is simple enough, and also the difference doesn't really matter, so this one will have a higher priority. And this one, on the other hand, is too complicated, talking about the same thing, why bother? So this one will be forgotten. Okay?
In this example, you are showing that independent variable became dependent.
No.
Can you
in this case, in all these 3 lines, what we are introducing are independent variable. Okay, this is one. The other one is the other way around. Okay, because you see, this again is symmetric. If I switch the order of the two, I'm going to get something. If something is P, then it's also X, also S to a certain degree. Okay, as I said, positive evidence is symmetric, negative will be not. So that's this one. And also, what's the third one? The third one is a comparison, say that kind of whether these two are equivalent to each other.
So we just check.
The dependent variable is actually here, which I haven't mentioned yet in my lecture.
So
Okay.
it is another variable.
Yeah, that's another one. You see, again, that's another major difference between variable and constant. All the swans in different sentences is pointing to the same concept. Okay? So constant name is kind of like a global in the system. No matter where, as soon as you use the same name, you're talking about the same thing. On the other hand, variable name are local, meaning that they only make sense in one sentence. So you have a variable called variable not one. Here you have another variable called variable one. They doesn't necessarily talking about the same thing. Okay, just like you in your formula, you have x in one line, you have x in another line. They can be talking about completely different things. Okay? Because it doesn't name a constant in their current form. They just it's kind of like a symbol or indicator of something to be determined later. Okay?
Oh, I have a short question. When we talk about a variable, so I mean it can be anything in the long-term memory base, or it can be anything only in a local memory base. So does that make a difference?
Yeah, that make a difference, but in the current situation, you can think that is referred to something in the long-term memory.
Yeah,
Okay.
anything is that in the memory.
Accurately speaking, not anything. That's actually another difference between my variable and the traditional universal variable. This actually means anything or everything in the domain, right? But this one is local in the sense that here I'm only talking about everything in the extension of this term. It's not really about everything in the domain. Okay. Here I'm saying that everything in the extension of S is also in the extension of P. So the field of evidence, so what is the evidence for this conclusion, is the extension of S. On the other hand, the evidence for this is the intension of P. And that's another principle of NARS. Never talk about everything. Okay? You don't have the knowledge or resource to say that, even for a variable. So this now we see this actually a way to separately talking about. You see, once again, it's the something I proved very early. I told you this is important. Now we go back to that again. We proved very early in this three are equivalent to each other. Okay? But this is a pure extensional version. This is a pure intensional version. Okay? And if we do it in binary logic, and then they're perfectly equivalent to each other. But when we turn it from here to here, because of the restriction of knowledge and resource, these three things, they actually correspond to these three things, okay? May have different truth value. And this is the extension version, intention version, and the combined version. Okay? But anyway, here I show you that the system can, by default, merge them, but if necessary, can separate them. That's actually the most fundamental reason for me to introduce variable in the first place. Okay? And that also means the variables are introduced in this system with restriction that is, it's kind of like it's only used to make this distinction. Again, that's another difference between my logic and the first-order predicate calculus, which allow a variable to be used in any position. For example, you can write this, right? in NARS, you say, oh, this is similar to that. You just say, okay, now I see what you mean. How about that? You never see this statement in NARS. Okay? Because it doesn't make sense in my context. What the real restriction is, you see, universal independent variable must appear in one sentence at least twice, and also on both sides of this relation for it to make sense. Okay? So you see, this is actually not a syntactic requirement. Syntactically, I can do this. Okay, it satisfies the grammar. It doesn't make sense. It doesn't make really any meaningful conclusion in this case. Because the very purpose of variable is to say that it will allow you to compare the extension of two terms or intension of two terms. To compare the extension of one term with the intention of another term typically doesn't make any sense at all. Okay? At least I haven't found any meaningful practical application which require me to do this. Okay? For the same reason, for example, this doesn't make sense. Okay? So you'll see that I don't really know, or I don't really want to make the grammar more complicated to add all those restrictions into it, even though I think it's possible. But it makes things too complicated. But you should understand.
But it looks like a pragmatic restriction.
You can also say that way. Yeah, pragmatic, maybe more accurate than semantic, but it's also kind of semantic. Because after all, this sentence is still talking about the relation between S and P. It just restricts the focus on how their extensions are related to each other. On the other hand, this is talking about how their intensions are related to each other. Okay? So that's for independent variable. Independent variable actually is used to capture this situation, to say whatever in this is also in this. Okay? Or whatever in this is also in this. On the other hand, dependent variable is talking about there is such a thing, or we are actually talking about this and this actually have some overlapping. The same thing for the intentional side. Okay? So for the dependent variable, the typical format or the meaningful format is to say that there is something which is both in the extension of S and in the extension of P. Or you can say it's in the intension of P and in the intention of S. In other words, this thing always appear on both sides of a conjunction. Both sides. Okay? And this one appear on both sides of implication or equivalence. Okay? That's the meaningful usage of it, no matter what the grammar allows. So that's this. Actually, when you go back to first order predicate calculus, you will see that even though it allows much more than this, most of the meaningful usage, okay, typically correspond to this two pattern tool. But of course, they only talk about the intention. There's extension. Only talk about extension. Intentional knowledge makes need to much more complicated representation. And these two are variations of this. As I already mentioned, you can also use the equivalence. And on this side, you see you can use the union intersection or extensional intersection and intentional intersection to combine these two statements into a single statement with a compound subject or predicate. It's basically the same thing. Okay. So again, literally speaking, this one only appeared once in this one, but since this one is a compound, that's basically the same as this. Okay. So that's the format and some summary. And also, this also related to an issue I said previously that can be handled, but I didn't mention how. That is how to derive negative conclusion using deduction. Okay. The previous rule only allow you to derive a strong positive conclusion, because if one of the premises is negative, the confidence value becomes very low, because the confidence value is all those things multiplied to each other. Okay, if one of them close to be 0, then this basically means I don't know. Okay? So how to get strong negative conclusion? Well, we can use the negation and the variable to turn it into kind of like positive. Okay, you see, this basically say that if for everything in the extension of S, it's not in the extension of P. So we can use the previously defined deduction rule. Okay, to use this as one premise. Another premise may be A is indeed in the extension of S. Okay. Then this one used together as a premise, you see clearly it derives not A in the extension of P. Okay. Sorry. With a high confidence. Okay. And then we use the negation rule also. You get something like this. So you can get strong negative conclusion using variable and negation. It's a little bit more complicated, right? But it can be done if necessary. Okay. So one major function of this layer is actually to use variable as a more complicated mechanism to fill in some gaps, okay, of the previous levels, which try to do things in a very simple way, even though that means some of the special case will need special treatment.
So another question, the two variables roughly correspond to two types of quantifiers in traditional logic. But in natural language, we have other quantifiers like a few, a lot, or many. How these kind of things can be represented in NARS?
Those things will be introduced as a special concepts. It's not a logical constant like this. Okay. You can say, later we will see, you can say that I have a sentence where there is a notion, this notion include a modifier which says a few. And then we will have to learn what a few usually means according to system's appearance in a certain domain. So we don't have a few or several defined in the system with a fixed meaning. You will have to learn that.
But are numbers or natural numbers learned in this meaning? Because when we talk about a few or many, it will naturally suppose that the system also needed to learn natural numbers.
Natural numbers, wait a minute. Okay, let me finish this. Just because mathematical knowledge is also introduced in this layer with the help of the variable terms. Okay, so we are going to talk about that and also some other related topic. But for now, I just want to make sure that you understand what these two types of variables intuitively means and how they're supposed to be used. Okay? They're supposed to be used kind of like as a supplement of this highly simplified representation about the relationship between two terms. So the intuition, yes, they share some intuition with fourth order calculus. No, they're not the same thing. Okay? It's not the same as this. And a lot of discussion in this chapter is about that. What's the similarity and what's the relationship? So now the new grammar rules. You see now a term can be a variable. A variable can either be an independent variable, a dependent variable, or a query variable. Okay. Here I still say that dependent variable you need to mention the dependency, but as I said later, you don't have to, so that each of them, you just need a special symbol to indicate what type of variable it is. Then you need a name. Why you need a name? Because in one sentence, later you will see you can have actually more than one variable. So you have to say which is which. Okay. So you just use the word just like the x, y, and 1, 2, 3. Yeah, now things become complicated. You see that if you have more than one variable, they can have also different kind of possible combinations. What if both of them are independent? If both of them are dependent, what if one depends on the other? What if one doesn't depend on the other? After I analyze, I believe there are actually only, if you limit the number of variables to 2, okay, there are actually only 4 meaningful combinations, which are listed here in a concrete example. So you see, this is the English translation. This is the corresponding NARS sentence. Once again, there is a truth value here. We just take the default, so I leave that out of the picture. Let's see one by one what they mean. So here we are talking about there is an open relation. Here, open means in this context a key open a lock. Okay. And then, if you want to say every key opens every lock. In NARS, you see, if X is a key, a concrete key, and Y is a lock, then X and Y has the open relation. Right? Now you should be able to understand this whole sentence according to what we have introduced before. So in this case, you see both of them are independent variable and they don't bound each other. And they're independent with each other. And the order of these two conditions doesn't really matter, which one you want to mention first. This order, of course, matters because open, A open B, B open A, that's a different thing in this context. The second sentence, there is a key that opens every lock. You see on top level, it is a conjunction of two sentences. First, you say, there is something called X, which is a key. Here, I'm not talking about every key. I'm talking about one specific key. So that's why this is a dependent variable, no matter how you mark it. Okay? And what? The second sentence itself is an implication. And if Y is a lock, you see here you cannot use X anymore because X is already used. Okay? You have to use a different variable name, whatever you pick. If Y is a lock, then X and Y has an open relation. And here X is one specific X, and Y on the other hand is independent. It's kind of like every Y which is a lock. Okay? So that's the second possible combination between the two. And the third one is, you see, the overall structure is an implication. This is the condition part. This is the consequence part, or conclusion part. Okay? The condition part say that if X is a key, then what? This part is a conjunction. Okay? There is a Y, which actually depends on X, which is a lock. And X and Y has this open relation. Here there is a dependency which which is the case because every key opens some lock, but that depends on the key. It doesn't open the same lock, right? Each key has its own lock that it can open. On the other hand, finally, we have just a three-component conjunction. Okay, there is a key and there is a lock, and the key open that lock. So which corresponds to the situation where you have two dependent variable. Okay, so you see this is two dependent variable, this is two independent variable, and the two middle ones are dependent and independent, but there are still two scenarios whether the dependent one depends on the independent one. Okay, it's complicated, but I believe it covers all meaningful combinations.
Why don't we write that in fourth sentences? In fourth sentence, why don't we indicate that y depends on x as we do in the third one?
You mean this one? Or you mean this one?
No, the last.
This one?
Yes.
This one, they doesn't depend on each other. We just say there are two different things. Okay? They just happen to be the case that the first one open the second one.
But x opens y.
Mm-hmm.
In the third sentence, we do indicate it, and in the fourth, we don't.
Yeah?
Why?
When you say something depends on something else, okay, the thing it depends on must be an independent variable for it to make sense. Two dependent variables don't depend on each other. This is the situation because basically this mechanism is used, mathematically speaking, to represent a function. Okay, if you have a function, we see this one depends on this one, but this one must be an independent variable by itself. It changes, so it changes accordingly. So that makes sense. Okay, if you have two things that both of them doesn't change, they just refer to different place. We don't say there is a function related. That's why there is no dependency in this case. Yeah, I don't want to go into too much, technical or logical or mathematical detail. I just hope you can see that these four sentences have different meaning. Okay, each of them contains two variables, but they have kind of different relation. Okay? And also, I believe whenever you have two variables, it's one of those patterns. If these two have some kind of relation, all the meaningful combinations are here. So my target in this level is if I can handle those things, I think this is good enough. Okay. Of course, you can have 3 or 4 variables, but that's kind of like unusual. In principle, there is no limit, but talking about our everyday life, usually we don't have many variables in one sentence. Just because it's very difficult to follow. Even those things, okay, some of you may think it's already a little bit confusing. Okay? But at least 2 variables will be necessary. Okay? We have other examples with those things if you check the file. Anyway, so this is still the grammar. Okay? How about the inference rules? So if some of the sentence contains variables, then the inference rules will need to be modified accordingly. Actually, I already used one without mentioning, without declaring it, just because it's pretty natural. Okay, well, let's see the simplest deduction situation, which is this. If you have something in S, implies that thing is in P, and this is indeed in S, then I guess we can derive that thing is also in P by deduction. Okay, hopefully you all agree with me. But this is not something can be covered by all the rules introduced so far. we need another one. But this one is kind of like quite straightforward. You see, we just need to allow x to be replaced by a. Why? Because this one say whatever in S is also in P and A is in S. It satisfies kind of intuitively the condition of the requirement. Okay? So if you say everything works, then A should work for this relation. After that, it's just a deduction rule. Right? So because this statement and this statement is the same statement, okay? So then that's derived as a result. So you'll see this just show you an example that all the inference rules we have introduced before can be used with the variable term with one small twist. That is, you need one additional step to replace the variable by a constant that satisfies the condition. Okay? And for those of you who are familiar with things like Prolog programming, this looks natural. That's just variable unification and variable instantiation. Okay? So to be accurate, this level doesn't really introduce any new inference rule. It just introduces one operation which is allowed, that is to replace one word, one term in a sentence by another term. It's called substitution, right? In logic programming and in many other domains. Okay? So in this case, we just say that we replace this by this. And after that, it's just business as usual. Okay? So whenever you do that, technically, in some literature, it's called variable elimination or instantiation. That is, you replace a variable by a constant. If the variable is an independent variable, that replacement is always allowed under the condition that the sentence satisfies the condition of being in the extension or intension of a given term as required by the other premise. Okay? So that's elimination. Introduction is the other way around. Later we will see. If this is the case, some of you may ask, where are the variables come in the first place? Well, I already showed you the rule in the previous layer 3 example. Okay? So you'll see that from this one and this one, the other way around, it actually introduces the variable into the conclusion of an induction. Okay? So again here, the rules are perfectly reversible. Okay? If you can do it in this way by deduction, you can do it the other way around by induction. And when you do deduction, you eliminate a variable. When you do induction, you introduce them. And that's where the variables come in the first place, in this system. Okay? So that's the two major things. So this is elimination. This is introduction. And then finally, there is a third one, which is either unification. That is, you rename a variable by another variable. Okay? In what situation that thing is needed? Well, let's see. It's very simple. How about this pattern? I have this sentence, then I have another sentence. If something is in M, is in P, and if something is in S, it is in M. Then what? Deduction, right? If something is in S, it is in P. Which looks just like an old-fashioned deduction by taking, this is one term, this is one term, this is one term, this is one term, and because this one are the same, and then the relation will be between this one and this one. But if you think it that way, you're wrong. Why? Because even though this M and this M are the same thing, this X and this X are not necessarily the same thing. right? As I said, if you have x in two formulas, they're not necessarily the same. So to be accurate, you should say this is variable number 1, this is variable number 2. Then you do a unification. Since every one in M and everything in M, they're talking about the same thing, I can rename the variable to make them the same. Okay? So it's kind of like I'm doing a unification by renaming both of them into variable number 3. I'm going to force them to become the same. After that, you can do this. Okay, whatever you call it doesn't really matter, whether number 3 or x or y. But you need to be careful. In this case, there is one step involved, which is called unification. That is, you unify two variables into the same. Whether you call it the first name or the second name, or you introduce another name, it doesn't matter. Okay, so that is, you see here I have some tables. In this case, I'm using this word, I say it's sample rules. Why? Because this is not a complete list. Why? Because there are other possibilities, but even though it fell into the same pattern. What if the variable appears as the predicate? That also can be eliminated. Okay, just to list all possibility will make the table too long. I will just say I'll give you a couple of samples. If you understand them, you should be able to understand all the rest. Okay. So also, after you add layer 6 into the system, you have to go back, kind of like to, if you really implement it layer by layer, okay? If you really do it that way, you have to go back to redo all the previous rules. Because in all the previous rules, what we required, as I said, syllogistic, right? There must be M in both premise for the inference to happen. Now, that thing is extended into the two premise must contain two terms which can be unified. It doesn't need to be identical. Okay? So to be unified means they can be, both of them are constant. If that's the case, they must have the same name. Or it can be a constant and an independent variable. Or it can be two independent variables which can be unified into each other. Okay? So that provides some challenge to the implementation. But conceptually speaking, it's actually pretty simple. Okay? So
is an example with the natural language possible of this statement?
later we will see, hopefully if I have the time, yeah, I'll give you an example of natural language. And also some of the natural language examples are already here. In today's lecture, you'll see toward the end, there are examples of level 6, okay, which contains English translations of all the variable related statements, a bunch of them, and including something more complicated than the one I just showed. And also, I show you step by step how to derive the log key example I just mentioned from simpler relationships. Okay? But to fully explain them will take a while, so we don't have the time for that. So these are the elimination rules. You see, they're typically the rules we introduced in layer 5. Okay, just now, some of the constant there are replaced by variables which will be unified with some other constants. Then you get the result. It's pretty easy to understand. Then this is the other way around. If you go backwards, you see, you take this as a premise, this is a premise, you get this as a conclusion. And then you get the induction and comparison rule, which introduce variable into the conclusion, where the premise themselves doesn't contain any variable. Okay? It's just how to make things more complicated if necessary.
Excuse me. Is this exactly the same you was explaining with evidence that is emitter, or is it for some other reason?
It's for exactly the same semantics, exactly the same definition of evidence. You see that in this example, what's the evidence that make this statement true?
I see.
You need to make this true and this true. Okay? And if I indeed have this true and this true, that's evidence for me to believe that. Okay? If this is true, but this one is false, then that's actually negative evidence for this one. Okay, and which is also captured by that function. Okay. So yes, the analyze in terms of evidential support is exactly the same as before. Okay. That's why you see I keep saying that each layer is a natural extension of the previous layers. All the decisions we made in layer 1 are fully respected all the way up. Okay, it's not like every layer is built by a completely different idea. That's not how this system, at least, is built. Okay. So, yeah, I didn't mention this yet. Dependent variable. That's slightly different. You'll see that for independent variable, and this one is talking about everything that you can replace it with a constant. Okay. On the other hand, independent variable, if I still use this format, you cannot handle it that way. Independent variable, if it doesn't depend on anything, is like an anonymous variable. There is such a thing, or there is something which satisfies a certain condition. But I cannot assume everyone does that. Okay? Just there is a special thing. From this information, I don't know which one. I just know there is somebody. Okay? So because of that, to replace this with A is not valid anymore according to the semantics. On the other hand, the other way around is valid. That is, if something is true for A, I can always say it's true for something, right? I can just turn every constant into an anonymous term. So this one and this one normally are the natural way of substitution. Use a variable to turn your independent thing into a constant, then you turn a constant into a dependent variable. If you do deduction, that's the only thing you allow. Induction, of course, is the other way around, so you can go backwards, but the conclusion cannot be strong because it's a guess or a hypothesis. Yeah? So this shows you, if M is in T1, also in T2, you can derive as M is in both T1 and T2, and also you can turn it into an anonymous term, say there is somebody, there is something which is in T1 and T2. Okay? Which is, as I mentioned, that's a common usage of dependent variable. That is, you say, these two things have something in common in their extension. That's how to derive that kind of conclusion. Okay? And this is the truth value function. That's how you calculate intersections. Okay? How about the other way around? This one is a little bit more complicated. Okay? They actually take two steps. So if you know something, there is something which is both T1 and T2. If now you know M is in T1, can you know M is in T2? Well, for sure you don't. Okay? But it gives you some evidence. Meaning that the detailed analysis, if there is something in T1 and T2, then T1 and T2 are similar to each other as far as that thing goes. Okay? If they're similar to each other to a certain degree, then one thing is in one of them, it gives you reason to believe it's also in the other. But the evidence is not too much. Okay? So this is kind of like two steps of inference merged into one, which I explain with some detail later. So Yeah, a whole bunch of discussions. And also you'll see the this log and the key example can actually be, the monster conclusion can actually be produced by the system itself. Oh, that's another principle of now in general. That is, everything, as far as it can be represented meaningfully in the system, there must be at least one inference rule that can produce it. That's a very important principle, okay? Because otherwise, there must be some knowledge which you can teach the system, you can code it into the system, but the system have no way to find it by itself, okay? If there is such a thing, then that basically means the system's inferential power is limited. So, as far as I can tell, that's not the case for the current design. Okay, whatever you can tell the system can get it by itself, under the condition that you give it proper evidence. Okay. So here I show you. This is not very easy to follow, but if you follow it, you will see that this two variable thing can be introduced by the system. All four combination can happen. Yeah. Now, that's basically the technical content of layer 6. Okay. After layer 6, also that's basically what I have already implemented in the current demo. That's from layer 1 to 6. Okay. To me, that's the relatively stable part of the whole system. In this layer, what we have, I believe we have something which is relatively complete with respect to declarative knowledge. That's something you can describe. Okay? And in the afternoon, we're going to talk about the top layer, which are beyond declarative knowledge. Declarative knowledge, roughly speaking, corresponds to whatever fourth-order predicate calculus can do. So I will say that to this layer is roughly correspond to fourth-order predicate calculus, but there is no, as you have already seen, there is no one-to-one sentence-level translation, just because the semantic assumptions are very different. And also this one allows a lot of uncertainty, which is not allowed in traditional logic. And also this one does non-deductive inference, which is not allowed in traditional logic. Okay? But in terms of expressing power, it's kind of like at the level of fourth-order predicate calculus and more. Okay? So to introduce a variable, one thing I mentioned is give the system the power to separate extension and intention. That's one function. Another function, also important, is to allow the system to do symbolic reasoning. What does that mean? That means the system can have a way to talk about concepts which doesn't really appear in its own experience. You see, in all the previous levels, all the terms about concrete things that must appear in its experience. Here, the system can begin to talk about some X which is not the real thing. Okay, it never really appear in the system's experience, but it has some property, which of course eventually related to the system's experience. Okay, so what the system can do in this case is to do abstract or hypothetical inference. That is, if something have this and this property, then it will have some other property, which is the very foundation of what? Mathematics. Idealize the situation, which you never experience, but you can think about. Okay, so you can talk about concepts like a point or a line, which ideally, you never see that. Okay? But as far as you can say, if such a thing have a certain property, blah, 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 and you can build that kind of concept in the system. Okay? So that's a discussion I have about symbolic reasoning in this part. But of course, I haven't built any concrete part of how to do that in the system, but that's where the basic idea is. Another thing, again, is something I know at the very beginning I need to take the challenge of. Is that not only mathematics is highly idealized, it's also axiomatic. What I have been doing from the very beginning is to do a non-axiomatic logic. Everything is true to a degree, then naturally people will say, how about 1 plus 1 equal to 2? That's absolute truth, right? You will have to allow absolute truth, well, otherwise your system cannot even do that. I will say yes and no once again. Okay? Actually, at the very beginning, I think I want to do something, use some kind of format to represent that, then give it a truth value of 1, 1. Okay? And not too bad because this is math. Okay? But later I changed that design. I will never allow that to be 1. Okay? But how to represent this? Not in this way, in a more complicated way. By doing what? By introducing abstract concepts. Okay? For example, I'm not going to have the time to talk about detail, but the basic idea is instead of representing this as a statement and talking about its truth value, I'm using this as a term. In a bigger statement, say that this sentence is a theorem in number theory. Okay? So that will be a higher order statement, including this one, just like as I said before, John knows, blah, 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 blah. Okay? You do it in that way. Okay? Then you have the concept of theorem and axioms.
Excuse me. Would be it represent like relation plus with two terms 1 and 1 and relation equals and so on?
Yeah, exactly like that. Yeah. You see, here I can have something like this. Okay, it's complicated, and that's why mathematics is complicated. Okay, so that the idea is not solve this at the statement level, but by introducing special concepts. So within my system, I can allow the notion of proof, the notion of definition, the notion of axioms, but each of them will be acquired concept that need to be learned by the system. So the system will learn there is such a thing called axioms. Each of them should be a statement, and that statement is assumed to be true. Be careful. Everything captured by the truth value indicates the things that is experienced to be true. Okay? Assumed to be true is a completely different thing. You never establish the truth value of this by observation. You don't. Okay? You take it either as an assumption or as a conclusion derived from accepted assumptions only, using the allowed inference step only. That's what we call proof. Okay? So once again, I don't really have a full example, but this is the idea about how the system learn mathematics. And also later we'll see that this also allows the system to learn different theory in mathematics. Okay? For example, geometry and also different type of geometry. And furthermore, it's the same idea. It will allow the system to learn different types of logic. Okay? Even though the system have a kind of like a built-in logic that's designed into it, it doesn't need to learn. It's born with all the rules. Okay? But everything else can be built on that. It's kind of like this is a native language. The system can learn any number of foreign language if you give it proper training. Okay? So here I have discussions about, for example, use this kind of like as a meta theory to support arbitrary logic or arbitrary formal language. Okay. For example, also knowledge representation, it doesn't really necessarily to be in this format. It can learn that for, say, first-order predicate calculus, it needs a special format. If you put a sequence in that order, it will be allowed as a well-formed formula, and you can talk about this truth value. Be careful, in that case, the truth value means truth in that theory. Okay, it's different from this truth value. This is true according to my experience. Okay? So the idea will become to use now as the common foundation of number theory that's learned by the system, probability theory. Even though the truth value function doesn't follow probability theory, the system can learn probability theory. Okay? By doing what? Just treat all the numbers as concepts, probability value as a concept, so that if you say probability of A is 0.3, then to this system, actually what it does is there is a relation between this A and 0.3, and this relation is a special case of a relation which is called probability assignment, right? Which allow you to assign a number to a statement. Okay. So to fully support probability calculation, of course, it will be more complicated than that. But in principle, I believe it can be done in this way. Okay. So you'll see this is the idea. That's what I mentioned. That at the very beginning, I mentioned what I call unified approach is for the whole system to use one single technology. That's this. But also at the same time, it allows other technology, like this, to be learned or to be built in, to be somehow connected to the system. And this, it can be anything. Okay? But the logic built into the system must be only one of them, just for the internal consistency, coherence of the system. That's my belief. But on the foundation of that, I don't mind the system to learn a lot of math. Okay? Each of them will be applied to a different situation.
Even in the human's case, for a pupil, a student who is not mathematically intelligent, to learn probability theory or mathematical knowledge is very complicated.
Yes.
Probably process underlying is very complicated.
Yes.
He learned the Bayesian theorem, for example, he does not know how to apply that.
Yeah.
He needed to know the meaning of that.
Yes.
So
Even AGI researchers make mistakes when they use probability.
how can NARS system
Learn from experience. Again. But there is no guarantee that system can learn any of those things perfectly. Yeah. It will make a mistake. But of course, for practical reason, this is actually not a very good idea to do. To teach it math is not really the most efficient idea. The most efficient idea, I'm going to talk about in the afternoon. The basic idea is don't learn math. Take a calculator with you. Whenever you do calculation, you just know which button to press. Use the calculator. Okay? But you need to learn a little bit of math. Okay? So that's kind of like the idea for you for actual application. But in principle, the system should be able to learn mathematics if it is given proper training. Or at least I hope this logic is enough to support the learning and the internal representation of other arbitrary formal system, even though the process will not be simple. Okay?
But that's a wrong question. Just a very simple sentence. There are, for example, 2 dozens of people sitting in this classroom. How can the system represent 2 dozens?
Well, there are several different ways. One possible way is you say something sitting somewhere. Basically, that's the relationship, the top-level relationship. Then you have more detailed description about what that something is. That something is a group of people. The number of that, the size of that group is a dozen. It's not one sentence anymore. Okay? It's a whole bunch of sentences.
So here doesn't look like another property.
Yeah. Yeah, you can do it that way. Or you can treat it as a property, or you can treat it as a relation between something and something else.
But traditional philosophers of mathematics will say, well, that kind of property is a higher order property. It's a type of type.
Yeah, it's just because they are using predicate calculus. Okay. Yeah. In this case, we don't have. Yes, if you say this is predicate, this is argument, then if you want to describe this, then you need higher order, right? But if I change this into this, they're on the same level. You can just add additional description about this one with no problem.
You said the size of the group is 24. But if we take individuals as the first level, the size of the group looks like the higher level?
Yes, but not in this sense. In this sense, higher level must means a statement of a statement. In your case, it's still a property of a concept. So they're still on the same level. Yeah. What higher level means in this model is different from what it means in predicate calculus. But anyway, I need to finish this pretty soon. So I said it can support other formal theory, which actually means two things to be accurate, or three things. As I said at the very beginning, a formal model means what? A knowledge representation language, some inference rules, and semantics. Okay, it should be able to support all of them. Especially that related to the issue of natural language processing. That is, the system should be able, you see, the native language is NARS, but they should be able to learn another language, okay, which can either be formal, artificial, or natural, like human language. How to do that? Well, currently I don't have that problem completely solved, but I have been recently start to work on that, and I have a paper for this year's AGI conference exactly on that, which is linked here. Too bad I don't really have the time to talk about that. But that gave you a motivation to attend the conference, right? So yeah, I will make a presentation to talk about that thing. The paper is, I think maybe it's already linked. Yeah. It's linked here. This is the actual testing example run in the system. You see here, I'm using two different types of terms. The all capital, now I'm using this to represent the internal name, which doesn't necessarily have anything to do with natural language representation. On the other hand, the lowercase names are actually English words. Okay, and this is the cat word. This is the cat concept, and the relation is what they call a represent relation. That is, this word represents this concept in a system. Different from many of the traditional work, this relation is not binary. It's true to a degree. That is, sometimes we use this to represent this, but not always. And also, it's many to many. That is, we can use many different words for the same concept, or we can use the same word for more than one concept in different situations. Okay? But anyway, so that's say what each word represents. And also, we can say this whole sentence or this sequence of words. Cat, eat, fish. Here, of course, I ignore a lot of stuff like plural and tense and so on. I say this whole thing represents this statement, which say that cat take a fish as food. Okay? Then if I give the system a whole bunch of things like that, eventually I can ask the system questions about the sentence they never seen before. For example, what is represented by dog eat meat? If you only know the given example. Okay, that's if you check the grammar, then that's what it means. Okay? And then I have a step-by-step process talking about how you see eventually the system know that according to its given knowledge, it kind of like basically use analogy, as you can guess. Okay? It use the given sentence to internal representation relationship as an example to try to guess what a new sentence means. Okay? Again, we don't have the time for detail, but that's basically my plan for natural language processing. And this is the very first step. What makes this approach very different from the traditional approach? There are several major points. One is you see clearly I don't have a separate NLP module in NARS which serve as user interface, something like that, like in most of the AGI project. Okay? Here, natural language processing is handled in exactly the same way as everything else. The only special thing is the data itself. Okay? The data involve some words and phrase and sentence as term. And also the relationship includes something like represent or whatever you call, which is special about language usage. But all the inference rules are exactly the ones we have covered before. Control mechanisms are the same. There is nothing special. Okay? So for NLP itself, if you check here again, the major difference is I don't have a separate, say, parsing, semantic mapping, and so on. Here, syntax, semantics, pragmatics are all combined together. That's basically, what you know about the concept of, for example, food. Okay? So the system will know that the food, use something as food, have some property, and also furthermore that relation can be represented by a word called eat in English. Then it will use that to do inference. Okay? Which I hope can explain why many native speakers doesn't really fully have a complete grammar theory, and they can still use the language reasonably well. Okay? Because they don't really need to systematically organize their linguistic knowledge. Instead, those knowledge may be specific to each individual word. I know how to use this phrase. I know how to use this word from my experience plus reasoning. I generalize them, but not necessarily to the level of, you have notions of nouns, of verbs, subject, predicate. Well, that will help, okay, especially it will help you to become a linguistics, but it probably not absolutely necessary for you to just use that language. Okay? So that's the thing I'm trying, and all the inference rules actually are the one that we have covered so far in the first 6 layers. So I think there is another paragraph which basically compares this logic with traditional logic. If you're a logician, you may be interested. Otherwise, I will not bother you with that. That's basically where I want to stop in the morning, so that's take a break, have lunch, and resume in 2 p.m. And then I'm going to talk about things I have not implemented, but covered in the book. Okay, I will see you in the afternoon.